Good morning, everyone. My name is Rustin Leno, and it's my honor to introduce Tony Hoare to you. Most of you might know Tony from his many achievements in computer science, like maybe you think of Quicksort, or maybe you think of the framework for verifying programs now known as Hoare logic, or maybe you'll think of CSP, or monitors, or conditional critical regions, or any of many other things. What you might not know is that Tony started in philosophy and had a passion in symbolic logic and the philosophy of science. So what he's going to do today is reflect on his experiences from both being a programmer and then entering academic life and thinking about science and engineering. And let me just add another note that Tony is also next Thursday going to give a much more detailed talk about unifying theories of data types, which is something that he's been thinking about lately. If you're interested in attending that talk as well, that'll be for a much more specialized audience, but in that case, let me know and I'll let you know where it is and you can come to. So without further ado, please help me welcome Tony.
Thank you very much. I don't usually correct people who've given me such a nice introduction, but the next week's talk is about data flow rather than data types. Sorry. Yes, I first got interested in philosophy when I was at school, and I read some works of Bertrand Russell, who impressed me greatly. Including his work on subjects like marriage and morals and so on. When I went to university, I got interested in modern symbolic logic of the kind that Russell used for his Principia Mathematica, and studied it from a book by Quine, the famous logician. It was quite I managed to get hold of the second edition of the book, and on the publisher's cover it extolled the merits of this edition of the book as compared with the first edition, and the publisher boasted that in this book, in the second edition, an inconsistency and other defects had been removed. I thought a logic book was rather a confession. Well, the reason I was interested in logic was because I think of the interest in philosophy, the interest in human understanding and human knowledge. One of Bertrand Russell's books was Human Knowledge, Its Scope and Limits. And it seemed to me, as to many other philosophers, that mathematics had a key to a level of certainty of knowledge that was not shared with any other science, and certainly not shared with our own common sense understanding of the world. So the analysis of the concept of mathematical proof, which is provided by the study of symbolic logic, seemed to be central to resolve the issue in question. And so that was how I came to think about program verification and the technology of doing it by means of assertions, which of course was due to Floyd rather than me. But the basic idea is actually using proof, and with the additional possibility that the proof could be checked by the computer itself. That was a long time ago, but since that time I've done work in industry and in academic research, in which I was required to fill in many research proposals for the available funding agencies. And the funding agencies all at the time that I was doing this work, were very insistent that the research should be applicable. It should be applicable to industrial needs and to commercial advantage. There was an explicit statement that the purpose of research is to advance the commercial success of the United Kingdom in international markets. And so practically every research grant proposal that I put in claimed that what I was doing had the potential of achieving that, and with the implication that it would be achieved shortly after the research had been completed. I'm now very ashamed of the claims that I made in those days, but of course in those days it was the only way to get grants, and particularly in computing, because computing is extraordinarily successful in satisfying industrial, commercial, and many other needs of humanity, which include now things like entertainment, control of shuttle taxis, and so on. And so the general atmosphere in which we were conducting research was very much as an engineering exercise, or we were being encouraged to regard it as an engineering exercise that would deliver benefits to British industry, primarily. And I think that has actually had an extremely damaging effect on the progress of computing science in general. First of all, of course, it immediately means that the whole conduct of science is an essentially national phenomenon. You will never get any international collaboration because we're all in the same competitive market. Why should the Americans help the British industry to achieve competitive advantage? So we're all fighting each other the whole time and not collaborating. But if you look at the really successful sciences, the mature sciences like physics and chemistry and astronomy, you'll see that they just don't have these constraints at all, and that they move ahead on their own schedule, and their only goal is the advancement of science itself. And any spin-offs are a separable concern from the actual conduct and the planning of the science itself. And the most important attribute of science is that it's cumulative, that the results obtained by one scientist are used by another scientist to make that second scientist's research more effective. You certainly see that effect in modern biology. The genetics project has achieved an exponential growth that is as fantastic as that which has been achieved in the development of hardware, simply because the results obtained and the tools built by the experimental tools which are built and used by previous scientists are refined and improved for use by subsequent scientists. The data that is collected by previous scientists, the catalogue of proteins and genes that have been discovered by genetics is accumulated in vast databases, and these databases are now an essential tool for every scientist. They underlie the planning of every experiment, and they provide a repository for ensuring the results of the experiment are useful to the later progress of science. And if you contrast that with the progress of computer science in the last, in the second half of the last century, perhaps one should say, it's a very stark contrast. We cannot really see the same kind of progress in computer science, the cumulative progress that we see so clearly now in other advanced branches of science. Oh yes, hello.
The other day I spoke to one of biochemists, and he told me that they would rather share toothbrushes than their data.
Is that still true?
It was true a few days ago.
2 days ago. Oh yeah, yes. Well, this is a phenomenon I have noticed. It happened in the early days of computer analysis of language and literature, that if you had a database that contained in machine-readable form all the works of Shakespeare, you did not share it with anybody else. I think that's disappeared. The controlling contract which governed the, I think the major part, certainly the later years of the Human Genome Project, had very strict rules about that. Nobody was allowed to patent the data. Nobody was allowed to conceal it for any longer than it took to check its accuracy. So publication was a religion in the project, and immediate publication. And I think that's the way scientists should be working together. Yes?
And when you talk about practical work, say, in physics, there was a time, say, during emergencies like during World War II, when the physicists did all kinds of practical things.
All kinds of collaboration.
No, practical work on your short-term.
Oh, right, yes, yes.
Now, would you say that work would delay scientific progress in the name of short-term expediency?
Actually, I think it had exactly the reverse effect.
I would expect so.
Yes.
So the question is whether the practical dimension is at odds with the long-term science.
No, this is the subject of my talk when I get round to it.
Okay.
Thanks for reminding me. Science and engineering. Engineering approach, sort of summarized, almost caricatured by the policy of the funding agencies in the last century, and the scientific approach, which is one that I will certainly recommend as a balance to the engineering approach. I'm not attacking engineering at all. We need it and we use it every day. But the case that I'm trying to make is that computing science is like other branches of science in that it does stretch. It has a pure branch in which the motivation for the research is curiosity and the advancement of science itself, and it has an applied branch which I don't really need to talk to you about because we both use the applications and produce them at Microsoft in an extremely exemplary fashion. But between the pure scientist and the practicing engineer, there's no direct divide because it's just a matter of scale. A pure scientist perhaps is more like a mathematician or a theoretical physicist. An engineering scientist one might define as a scientist who chooses his subject of study from a branch of science which is relevant to engineering. So I think I would like to show to you that computing science is an engineering science, that it's relevant to engineering, but that it has a pure side to it which makes it into a science. And then, of course, there's the scientific engineer, the engineer who uses scientific understanding, scientific theories, calculations and methods to help in the engineering, particularly in projects which actually require a certain amount of innovation that goes beyond the standard engineering benchmarks and best practices. And then the practicing engineer who just gets on with the job and doesn't worry too much about the science. So it's because there is this spectrum that I think we can say that computing science is a branch of science, and that software engineering is a branch of engineering. And I think if one gave the answer no to either of those questions, you would have to give the answer no to the other. Because I think by engineering, these days one understands a practice which is based on science, which uses scientific results and calculations. Similarly, the scientist regards engineering application as one of the most convincing experiments for the validity of the understanding that has been gained by the research. So let's see, I'm going to begin with to emphasize the range of that gap. That although an individual person may have activities at any point in that range, I shall emphasize the differences rather than the similarities and the connections. And I'll assume that we're talking about the purest of pure scientists, and I'll call him a he, and we're talking about the most engaged and practicing engineer, and she happens to be a woman. Well, the first thing is the time scales. The scientist works for posterity. The knowledge and understanding gained by scientific research is intended to have permanent validity. It's never going to go out of fashion. It's never going to lose market share. And it's never, the scientist hopes certainly that it will be a long time before it is superseded or refuted by subsequent experiment. Engineering tends to be much more short-term. In fact, to have a fixed timescale. An engineering project usually has a delivery date, actually the delivery date puts a frame on what the engineer can do that makes the engineering really possible. It's impossible to do engineering without hopefully a fixed but a fairly firm delivery date, because every decision is based on what can be done now rather than what can be done in 20 years' time. Science is driven by idealism. Scientists look for absolutes. For example, a measurement scientist tries to improve the accuracy of measurement as far as possible. There's no a priori limit on how accurate he wants measurements to be. The chemist wants pure materials, so that the art of purification is very, very important. The mathematician wants certainly to have sound theorems. The engineer, on the other hand, is constantly faced with compromise and has to work out an adequate way of doing something which may be very far from the ideal. And she uses her experience and her abilities to find compromises that are appropriate for the very particular project that she's currently engaged in. Certainty. The scientist is looking for certainty. Every scientific result should be backed up by a convincing evidence, very often in the form of an experiment, which demonstrates the application of the theory to some a physical phenomenon or range of physical phenomena. And the scientists will go on collecting evidence for the theories, for the important and fundamental theories of the subject, far beyond any real reasonable doubt that anybody could have that the theories are correct. If a physicist discovers a new way of testing the validity of, shall we say, the general theory of relativity, he'll perform the experiment. Nobody doubts the general theory of relativity, but the more diverse experiments you have that support it, the better. Engineer can't afford certainty. So engineer works in the real world. It's full of doubt and confusion, and the only thing the engineer can do is to collect whatever evidence is reasonably and quickly available, and then manage the risks that are incurred if their judgments are incorrect. The scientist is seeking perfection, as I've said. For the engineer, adequacy is always enough. Good enough is good enough, and you do not spend extra time and effort making something perfect if what you already have will serve the particular needs of this client or this particular marketplace. The scientist is seeking generality. The scientist wants theories that explain as wide a range of phenomena as possible. The engineer is not interested in generality. The engineer wants a solution for this specific problem, and it doesn't have to be generalizable to other similar problems. This is why engineering itself is not cumulative. It's because all the decisions taken are local to the particular customers and particular marketplace, particular technology, particular products. And the next time a project arises in the same area, you cannot reuse those decisions and those judgments and those calculations and those results. The scientist attempts to separate concerns. If it is known that the results of an experiment depend on temperature or velocity or what, every factor on which the result depends is separated out and controlled independently. Preferably they are kept as constant as possible, so that only the interesting variations are explored. The engineer is concerned with exactly the opposite. It is the integration of concerns that is the job of the engineer. Many products require an understanding or apply the results of many branches of science, and the engineer has to have a sufficient range of knowledge and at least a superficial understanding of all the branches of science that are relevant to the design of a particular product. And little snippets of information from all over the place are assembled together and form the basis for the design of the next project or product. The attitude of the scientist to originality is very different from that of the engineer. The scientist seeks originality and abominates copying, plagiarism. So originality of the scientific result means that it is contributing to the progress of science as a whole and not just repeating things that have been done before. So if somebody is discovered to have plagiarized their claimed results, then they are more or less excluded from the scientific community from then on. The engineer hates originality. Originality means taking risks, means doing something new. The engineer will be original only under the utmost requirement of the particular project on which they're working. And originality only in one aspect of that project. Engineering projects that try to innovate over the whole of a single product are almost inevitably going to fail. One at a time is, and if an engineer overdoes the originality, if an engineer deviates from what is tried and true, what is already established as best practice, maybe even incorporated in standard procedures, some of which are legally enforced, and if she diverges from those, she too will be excluded from society. She will be put in prison. So there are some very severe constraints on the engineer's use of originality. Formality. The scientist loves formality. He wants to reduce everything to a mathematical formula. And of course, the ideal is preferably a very short formula. E equals mc squared. Gosh, I haven't seen a formula as short as that in a computing science paper since... can anybody help you? Have you ever seen a formula in a computer science paper as short as that? But still, we do value neat, elegant presentations of theory in formal terms, from which we can draw, which we can use to calculate, to transform and calculate using mathematics. The engineer's attitude to formality, again, is exactly the opposite. She hates formality. She had to, if she went to a good engineering school, of course, she was forced to study mathematics in her degree courses. But she didn't like it then, and she likes it even less now. So fortunately, the engineer relies on experience, on intuition, on understanding, somehow an intuitive understanding of the physics and the reality of the situation in the real world, which actually goes way beyond what could ever possibly be formalized. And intuition is developed by experience and by some capacity of the human brain that we really don't understand at all. Well, we can probably only explain it by evolution rather than by understanding the mechanisms. So I'm suggesting that for computing science, we should regard the ideals of perfection that are characteristic of science could be summarized under the title correctness of programs. At least, shall I be talking about myself rather than all of us? We want the programs to be absolutely correct. We don't want them just to be correct enough. And in the search for and elaboration of the concept of absolute correctness, and in the means of achieving it, we learn so much that is going to be useful in making programs more correct. It's not an absolute, but at least the knowledge is applied in a way that always falls short of the ideal. So I'm very happy that the verification technology, which I have regarded as resulting from a pursuit of perfection, is now widely used for bug detection, for defect detection rather than defect prevention. Because that's what an engineer is supposed to do, make things better. Don't wait until they are perfect. Otherwise we would all still be waiting. The practicing engineer has another obligation, and that is that the product delivered to a particular customer or into a particular marketplace should actually be useful and dependable in the circumstances of its use. It has got to correspond to the needs of the users and the fault modes in the real world which sometimes prevent those needs from being met. So dependability is essentially in the province of the engineer, because the product is dependable in its use by a particular customer in a particular range of circumstances which do not generalize in the way that total correctness does in the case of programs. And dependability is a very much wider and very much more difficult to do scientific research in dependability, because dependability is all about adapting to particular circumstances. And by definition, science hates particular circumstances. It's looking for generality, reproducibility the whole time. Oh, that's a pretty long list. I mean, is it surprising that scientists and engineers sometimes don't communicate, or don't communicate in such a friendly fashion as we might hope for? They are really, at the extreme, they could occupy extreme positions in that spectrum. And I think the recognition of the cultural and emotional and personal differences between the two ends of the scale will help us to achieve, paradoxically help us to achieve, what is really one of the most exciting features about conducting science in an engineering domain, that we can learn from what the engineers do, as well as the engineers can use our results to do it better. But it requires a chain of perhaps different people to achieve that communication. Technology transfer is a process involving quite a long community of people, each of which contribute to it at a different point in the spectrum. Of course, I've been talking about a he and a she, two different people. Many of you, many people in Microsoft move between science and development, either short distance or indeed completely moving out from research division into the development division, or and sometimes vice versa, backwards. And that, I think, gives to the individual the chance to really explore the entire span of interaction between science and engineering. That's something which is really delightful to see actually happening at Microsoft. And I think, well, may be one of the main reasons for success. In the remainder of my talk, if you are interested, I could just give you a brief summary of why I think computing science is a science, because actually there are many people out there who doubt it. There are many people who regard it as pure engineering. And I think that our very success has contributed to the general belief that all we do is to write programs. The enormous benefits that software has delivered to the world, I don't have to go through them, suggest that most people's contact with computers and with software is very much through the practical product end. So I think we need to make a case that computing is a science, and we do so by pointing out similarities with other branches of science. Every branch of science chooses, the different branches are based on a choice of different subject matter for study. Biologists study animals, botanists study plants, and of course most of them study just this one species. Whatever it is that they study, they ask various basic questions about it. The first question that they ask is what is it? What does it look like and what does it do? And in the early stages of biology, which if you recall goes back to Aristotle at least, descriptive and classificatory biology was the way in which the subject was studied. So of all the various species of animal and plant, they were able to describe, obviously with the aid of pictures, the external and internal appearance, or shall I say first the external and then the internal appearance and behavior of the object. So we could say the same thing about computer programs. We need to study what they do. I think the general public is rather surprised that we don't know what the programs do. But none of you are surprised. Even the programs we wrote last week, we don't know what they do. How does it work? Well, this is now the science progresses onto a more analytic rather than descriptive phase, and it attempts to look inside the external appearance of the object, to split the object up into various parts and explore how the parts interact with each other. So a description and answers to the questions, how does it work, are usually expressed as a sort of divide and conquer technique. You describe the individual parts of the organism or motor car or whatever it is you're studying, and then you explore how those various parts interact. And when you understand that, you then have advanced your understanding of the subject matter of your study. You've advanced the science. The next stage is an even deeper question. It arises out of the second phase. You ask, why does it work? And the answer to that really involves the development of theory. It's the theory that tells you why it is that an assembly of components interacting across a collection of interfaces is going to produce the kind of shapes and observations and behavior that was discovered right at the beginning of how the organism or the product actually behaves. So the scientist is interested in saying, oh yes, if you build it, any product that you build with this kind of interface between these kinds of components is going to behave like that. And this is what is studied by the theory of programming, theory and programming language semantics. And finally, the question is, how do we know? I think the answer that I give to this is, how do we know that the answers to all our previous questions is correct? I'm going to suggest that proof of correctness of those answers is an appropriate way of progressing it. And furthermore, that the computer itself can check the validity of the proof. So when we ask the question, is this a correct description of the behavior of this program? Or perhaps the sort of backward, in some ways, better question, is this program design actually going to meet this description as its specification? Then a proof that it does so is, particularly if the proof is checked by computer, it gives us the same kind of assurance that the program meets its specification as we have in mathematical theorems. In other words, in principle, in the ideal, we can regard the conclusions drawn by the application of our research as being as certain as the truths of mathematics. It's a pretty far-fetched ideal, but there are many researchers who are pursuing it at various levels of idealism, including many from Microsoft. I think I've... So how are we going... I don't have to give this slide here. How are we going to deliver the results of this almost pure research into engineering practice? It's going to be in the same way that all other branches of science deliver their results to every other branch of engineering. Engineers don't do science anymore, they get the computer to do it. They don't do calculations anymore, because the computer does all the calculations. And the scientific theories are delivered to the engineer, and increasingly now to other scientists even, not in the form of published papers, although of course there are many good publications as well. The actual delivery is in the form of a computer program. Mathematica, for example, Simulink, MATLAB, there is what's the standard statistics package, and they mean that the user of mathematics, the engineer or the user of statistics, doesn't really have to do all those finger exercises. They don't have to do symbolic integration anymore. And the same is true of in a specific branch of engineering, there will also be a set of very specific design tools, design automation tools. Some of them will be checking tools that, for example, check the integrity of a structure, but others increasingly will be design tools which do a continuous check and make sure that you can't even draw a picture of a building that's going to fall down. And I think we are already finding in Microsoft that these tools are being used by our engineering colleagues. Oh, summary. In science, we can see the range of another range where the science of correctness, which has been the subject of my own research for many years, leads to the design of the construction of design automation tools, perhaps specialized to particular application areas. This is beginning to happen in the embedded systems industry, where specialized tools are being used to develop quite large parts of aircraft and rockets and train signaling systems and so on. They tend to be somewhat specialized to the application. And program analysis tools like SLAM or even prefix and prefast are towards the lower end of what we hope one day the tools will be able to do. And the engineering of dependability, which is actually making products that the marketplace wants or which the client is willing to pay for, that will always be an engineering subject. It will rely on the qualities of engineers that will never be automated, their understanding of the real world, their understanding of other people, their intuitive understanding of the technology and what is available in the established technology, and there's no fear that any good developers or programmers will ever be thrown out of a job by automation, by automatic tools, because the tools are going to be useless or even counterproductive unless they are applied to real requirements in the real world, and which have been discovered and controlled by the engineer, not by the scientist. That's, I think, all I have. Thank you. Oh, this is my dream. If one day, this is the scientist talking, the scientist seeking ideals, that software will be the most reliable component of every product which contains it. Because if every program has been proved to do what it's supposed to do, there's no reason why it should ever go wrong. Software engineering will be the most dependable of engineering professions, because what we do is actually subject to mathematical proof, and we don't have to rely on intuition and guesswork to make sure that our products are free of defect. And we will achieve these goals because the scientists and engineers actually cover the full spectrum of crossing the gap between the cultural boundaries which separate them. And let's face it, the way that this is actually happening in Microsoft for the last 10 years since I joined the company has been an amazing inspiration. If I've done anything, I've just summarized what I have seen going on around me every time I visit Redmond. Thank you.
Some questions? Did you?
Yes.
I wonder what you think the world would be like if we were held professionally liable for defects in our work, like garage mechanics, rather than it doesn't matter, like novelists.
I've often speculated about this. That there should be a law which made people professionally accountable, and I think that will happen, but it mustn't happen too soon. I expect you would say, well, it can't happen too soon. It should have happened already. No, the professional and other liabilities can only be instituted and enforced in an area in which there is built up a body of standard practice. And you can't force that to happen by premature legislation. I think, and particularly these days, you can't ask engineers to do things for which the tools are not yet available. When it becomes a relatively easy thing to perform the kinds of checks and adopt the kinds of development procedures that lead to reliable software, then the law can be enforced. So it's a bit like seat belts and drink driving and speed cameras. The technology has got to be there before you can legislate. Furthermore, the culture has to change. Now, legislation is a big break point where the culture can change quite rapidly. I mean, I think it's really only taken three or 4 years for the culture of wearing seatbelts to become absolutely. But that was only possible because they delayed making them a legal requirement for at least 15 years after it was known that they would be beneficial. So I think, yes, one day these things will be, it will be a matter of professional accountability, but there's still a lot of research and development to do before that can be enforced. Yes.
I don't want to offer a prediction, but just to point out that there is an alternative. Like in physics, you cannot measure beyond Planck constant.
Yes.
So in software, starting from certain size, forget about growing. The size may grow, but the phenomenon may be part of kind of large numbers for computer science. Like you have large numbers in probability, you may have such a law of large numbers in computing.
I think that's perfectly right. And quantum physics is one of the most broadly evidence. The evidence for the validity of quantum theory is enormous. But you wouldn't use quantum theory for building a bridge. It's not much use in engineering at all. There are many stages where you lose that degree of certainty. Actually, the point you're making is different. Quantum theory is the fundamental imprecision, which quantum theory says we can never, is an impossibility result, and it's only one example of other impossibility results that lie at the basis of many other branches of science, including our own. You know perfectly well what I'm referring to. So we're always working on this side of computability, but nevertheless, most of the time we forget it. And we can validly do so in just the same way that the physicists seeking to improve the art of measurement knows that it can't be done perfectly, but otherwise sets no bound on the accuracy which he is seeking. Yes.
Today we find that an increasingly large number of important programs like search and speech recognition, etc., are actually statistical in nature.
Yes.
So it could be argued that software will only be as reliable as the data that it's using to model.
Absolutely, yes. I think every company knows what it's like to operate the company when the database data in the database becomes suspect. It's a nightmare. That's right. And if you work in reliability, or indeed more or less anywhere in modern society, you have to realize that you are only tackling one very small part of a very much larger problem. And however fascinating it is to work in program correctness, It's just part of a chain, all of whose links have to be reliable. This is why I was rather careful on this slide. I didn't say that the software would be completely reliable. It's just that instead of being the first component of the product which everybody suspects, it's the last. And then I think we'll have done our job.
I was thinking that scientists are concerned about correctness and engineers are often concerned about time.
Yes.
Like delivery time. So the engineers are very excited by the formal tools because they can ship sooner.
Absolutely. I think that's another development which I've seen in the last 10 years, that when the scientist talks to the engineer, the most effective way of getting new innovation accepted, it's always going to be a difficult job, is not to try to frighten them with the consequences of an incorrect program, which we know can be quite severe. I mean, billions of dollars have been lost. Because it happens so rarely, it doesn't affect people's behavior to realize that there is a risk of that magnitude lurking in millions of places inside the code that they're using or producing. But the argument for cost is a much more convincing one and a much more scientific one, and does not require big steps in the technology transfer. It's possible to test whether a change in procedures or in tools is actually helping to increase productivity or the reverse. It isn't an enormous investment which you then have to throw away if it doesn't work. So it makes the transfer into a gradual and evaluable process. We must keep more statistics about how much things cost. I saw an estimate produced by the US Department of Commerce that suggested, on, I think, a somewhat dubious extrapolation, that the US economy was losing something like $50 billion a year on software error, of which 40% was the cost of the error to the person who developed the software, and 60% was suffered by the users. The suffering was not just in the direct consequences of an error, but all the extra work that everybody goes through to protect against the possibility of error. So, well, I mean, I'm sure I spend at least 5 minutes a day wiping the computer's nose in some way that is connected with making sure it's secure. Now, 5 minutes a day for 1 billion users is actually a lot of money. But we must keep a sense of proportion, even if we extrapolate to the whole world and suggest that the cost to the world economy of software error is $100 billion a year. That's the same as the cost of lower back pain. The cost of lower back pain is partly in the actual medical costs of treating it, and partly in the days of work lost to the economy as a result of it. And it probably comes to about the same as the cost of software error. So, but software error is a form of lower back pain, isn't it? You come to think of it.
So you laid out very capably the difference between scientists and engineering, and if we look at university programs, we see that division usually very concretely stated. So most colleges have a formal physics program, and then electrical engineering, applied material science, or materials engineering.
Yes.
Obviously software engineering, a less mature discipline, we don't see that division as concrete, or to put it another way, looking at most of the developers coming in from college, many software engineers at Microsoft had a background, a degree in computer science. And so I'm wondering if you see the day-to-day or longer term at Microsoft lasting effects of people who weren't really trained as engineers, who may be trained as scientists, dealing with engineering problems and perhaps not dealing with them as capably as our brothers in other disciplines.
Yes, I think one of the nice things about computer science is that the actual writing of programs and the theory of how they work can both be taught in the same university course. Well, the second of those would almost certainly be an option. And maybe it's because of that that we have tended not to realize how big a gap there is between engineers and scientists. The other thing is actually a scientific training is not a bad training for an engineer. I mean, I trained as a philosopher, and I don't regard that as a bad training for being a computer scientist. So I don't know how things will develop based on the kind of analysis that I've been doing. I suspect I would regret splitting them too much. I think every course has got to cover a significant part of that range. That is, one problem with software engineering, has got associated with the soft sciences. So you learn. I don't think against the soft sciences, but it's not. They're not engineering, in our sense of the word. So I don't think it matters that computer scientists are where we recruit from. They will find their own position on the scale, and they will move that position during their career anyway. Good. Well, that's a question I haven't had before, so my answer is both rambling and new. Thank you.
Anything else? So you gave the profiles of scientists and engineers, and are you saying that should be discouraged somehow?
Should be
discouraged.
No.
So that
No.
There shouldn't be such a clear difference.
No, I think it should be encouraged. Yes, because progress is made by the interactions of diverse cultures. All innovation is based on the fact that at some point in that chain there had been a gap and they found a way of bridging it.
Yeah, there should be someone who can bridge that, and that person should be half scientist and
That's I think we have a wonderful capacity as human beings of being able to split ourselves in half. But you should know when you're doing it. And if you recognize the breadth of that range and identify where on it you are currently positioned, because you're likely to move, then when you talk with somebody who occupies a slightly different position or even a diametrically different position on the scale, you can both understand the other's point of view, and that understanding will lead to the understanding which enables you to interact in an innovative kind of way. So what I'm objecting to is having them both pushed too close together. That the funding agencies think that all scientists ought to be engineers. Let's recognize diversity when we see it. We're willing to accept diversity in gender and race and religion and all these. In fact, it's even encouraged by law. Perhaps we should have similar respect for diversity in the range of intellectual disciplines that lie between pure science and engineering.
All right. So let's see. So we're going to thank Tony, but just afterwards there will be a short announcement by Shamsi. But let's thank Tony first.